Welcome to my channel. In this video, we shall be looking at circular motion. Circular motion is what we are looking at. Let's look at the learning outcome. Learning outcome. At the end of this video, you will learn the following: circular motion, uniform circular motion, non-uniform circular motion. You will understand angular velocity. You will know the relationship between linear and angular velocity. Relationship between linear and angular acceleration. You will know what is period and frequency. You will understand centripetal acceleration, centripetal force, and practical application of centripetal force. Circular motion is the motion of an object or particle along a curved path. The motion of an object or particle along a curved path. If you have an object moving along a curved path like this, we can say that the object is undergoing circular motion. And to describe circular motion, the familiar definition of displacement, velocity, and acceleration are used, with emphasis on angles instead of distance. In my earlier video, we looked at concept of motion, and there talked about displacement, velocity, acceleration, and other terms commonly used in motion. So I suggest you watch that video to understand more. So these terms that we use in motion, under linear motion, motion on a straight line, is similar to what we are using in circular motion here. However, the emphasis in circular motion here will be on angle. So we shall be talking of angular displacement, angular velocity, angular acceleration. Are we together? Because the circular motion is in respect to angle. So here we'll be talking more about what? Angle than in the case of the linear motion. So circular motion occur mostly with rigid object. Object that is rigid object or body. For instance, this is a rigid object. It's not with fluid like liquid, gas. So circular motion is associated with rigid objects or bodies. Okay, let's make progress. And what is a rigid object or a rigid body? A rigid body is one in which the distance between 2 points of the body remain the same when the body is translated or rotated. So if you have an object, for instance, if you have, let's say, this marker, if you have it, if you try to rotate it, you discover that the distance between 2 points remain the same, irrespective of how you rotate or transfer it. So we can refer this to be a rigid body. So we have seen the definition of a rigid body. Unlike liquid, if you have water, let's say in a container, as you try to rotate the water, you discover that the particle will be displaced from each position. So fluid is not considered as rigid body or rigid object. So in all we shall be discussing, our emphasis will be on rigid object, which is an object in which the distance between 2 points on the object remains the same when the body is translated or rotated. Okay, let's make progress. Having known what circular motion is all about, we want to look at uniform circular motion. Uniform circular motion. For instance, if you carry a stone, tie a rope to it, and you hold it with your hands, and you wind it. you discover that the stone will move in a circular position. So if this is my hand, tie a rope to a rigid object, and as you try to rotate, discover that the stone will move in a circular direction, giving us something like this. So as the stone is moving, it has moving with velocity, and it has an acceleration, radial acceleration. So at each point you look at the stone, it's moving with velocity, moving with radial acceleration. And from here, we can say that if we consider this point B, where the stone is moving with velocity V, consider the center O, then we will see that as the stone is moving at an angle. Let's call the angle theta. The angle keeps changing as the stone moves from point A, moving in velocity V, continue to move covering a distance x. So this is the distance it moves. So the angle keeps changing as the stone keep moving. So this demonstrates a uniform circular motion in horizontal plane. So uniform circular motion in horizontal plane. So as we can see, okay, the length covered by the stone, let's look at it. The length covered by the stone as it moves is equal to the arc AB, and is given by the length S of the arc AB is given by S equal to R change in angle. Let's call this equation 1. So this is the R, is the distance from the center, is the radius. So this distance covered is equal to R times change in the angle. So an object traveling in a cycle at a constant speed is said to be exhibiting uniform circular motion. So what is uniform circular motion? Uniform circular motion is the motion of an object traveling in a cycle at constant speed. So if an object is moving in a cycle at constant speed, we say that the object is undergoing uniform circular motion. Okay, having known what uniform circular motion is all about, let's look at non-uniform circular motion. Non-uniform circular motion. When the angular velocity of an object moving in circular path changes with time, the object is said to undergo non-uniform circular motion. So for an object moving in a circular path, if the angular velocity changes with time, as the object moves along the path, we say that it is undergoing non-uniform circular motion. So let's look at, for an object undergoing non-uniform circular motion, you have an object moving with velocity v, radial acceleration ar. At one point, as the object moves, velocity v, radial acceleration ar. At another point, velocity v, radial acceleration ar. So this is an example of an object, and as the object is moving, we have what we call tangential acceleration, represented by at. So we have that the acceleration of an object moving in a non-uniform circular motion is equal to ar squared plus at squared. Let's call this equation 2. So this is a diagram showing non-uniform non-uniform circular motion. So, and we have said that an object undergoing non-uniform circular motion, that the angular velocity keep changing with time. So, an object undergoing non-uniform circular motion has two components of acceleration. We have the radial acceleration that is directed towards the center, even like we have in the case of a uniform circular motion. Then the other acceleration that we have is tangential acceleration at a point which we call tangential acceleration. So the total acceleration for an object undergoing non-uniform circular motion is given by equation 2. Okay, I hope you understand, you are following. Okay, let's make progress. The next thing we want to look at is angular displacement and angular velocity. Angular displacement and angular velocity. I told us before that our emphasis under circular motion will be in terms of angle. So we are looking at angular displacement and angular velocity. An angular displacement is the angle through which an object turns. An angle through which an object turns is called angular displacement. Example, like the DVD player. Discover as you put the cassette, it will be turning, and in the process, music, videos will be playing. So an object that an angular displacement is the angle through which an object turns. For instance, you have an object initially at a point, let's say X, and is being displayed through an angle theta I when it's at a point Ri, and at another point is being displayed to another position. Is being displayed to another position having theta F. So this is the total angle that it has moved. So it has moved to another RF. So through this, we say the angle through which an object turns is called angular displacement. So you have an object initially at a point X, is being displayed to another point Ri, covering an angle theta I, and is displayed further to another point Rf, covering an angle theta F. So we can say that the angular displacement is equal to theta F minus theta I. Let's call this equation 3. So this is the angular displacement, the angle in which an object turns. Object initially at a point, turn and to another point. So the angle through which it turns, we call it angular displacement. So angular position is measured counterclockwise from the reference point. If you observe the object initially here, so as it is rotating, we are measuring this way. So this is counterclockwise. Let me bring it here. Okay, this is counterclockwise. Why, if it goes this way, this one is clockwise. So we are saying that in angular motion, we go counterclockwise. So here, this is clockwise. Why, if you go this way, is counterclockwise. And for counterclockwise, the angular displacement change in theta is positive. While for clockwise, change in theta is negative. I hope we are following. So all we are saying is that, the way the clock move is, the clock move this way. So this is clockwise. Are we together? Okay, so we are saying that in circular motion, the angular displacement is counterclockwise. And for this, the angular displacement is positive for counterclockwise, while for clockwise, the angular displacement is negative. So let's take note. So we have change in theta is positive for what? Counterclockwise, while for clockwise, the angular displacement is negative for clockwise. So we shall be following this as we make progress. Okay, the next thing we are looking at is average angular velocity. Average angular velocity. Average angular velocity represented with given by this is given by the expression average angular velocity is equal to change in angular displacement over change in time. Let's call this equation 4. So this is our average, this is the average angular velocity. Okay, let's look at instantaneous angular velocity. Instantaneous angular velocity is equal to limit as change in time approaches 0, change in displacement over change in time. Let's call this equation 5. So this is the instantaneous angular velocity. This is the expression for it. The next thing we want to look at is relationship between linear and angular velocity. Relationship between linear and angular velocity. So we are looking at relationship between linear and angular velocity. Okay, if you have an object that moves from one point to another, covering a distance x, and as well as angle theta. So we can have that distance s is equal to r change in angular displacement, which will be equal to r theta f minus theta r. Then average linear velocity is equal to distance over time. So we call this equation 6. So from this diagram, we are saying that distance, you have an object that covers an angle of this and distance this. So the object moves for it to cover this, the change in angle is final angle minus initial angle, like we have seen before now. So we have that linear average velocity is equal to distance over time. So in place of this, we can substitute this expression. And if we do that, we will have what? R times theta f theta I over change in time. But we have earlier seen before now change in angular displacement over change in time is equal to, is the average angular velocity. Remember, we got equation 3 for angular velocity to be change in angular displacement over change in time. So if we apply this here, we will have our change in angular displacement over change in time. So, but this is equal to average angular velocity. So let's call this, if this is equation 7 and this is equation 8, from here we can have that average linear velocity is equal to, in place of this, we are substituting this. Are we following? So it will be r angular velocity. So let's call this equation 9. So we are looking at relationship between linear and angular velocity. This is the relationship. This is the linear velocity, this is the distance, and this is the angular velocity. So this is the relationship between linear velocity and angular velocity. This v, average angular velocity, the unit is meter per seconds, and omega, which is the average angular velocity, is in radians per second. You see the difference? Radians, unit for angle. Meter, unit for length. Are we together? So this is the relationship between linear velocity and angular velocity. Okay, let's look at a similar relationship for in terms of acceleration. Is there any relationship between linear acceleration, linear and angular acceleration? An object in non-uniform circular motion has a changing speed and a changing angular velocity. We have established that before now, the object moving in a circular path with changing average velocity is said to undergo non-uniform circular motion. So an object in non-uniform circular motion has a changing speed and a changing angular velocity. So we have angular velocity, a changing angular velocity to be omega 2 minus omega 1. And if we have the change in time to be t2 minus t1, then average linear acceleration will be equal to change in angular velocity over change in time. So this will give us change in angular velocity, change in time. So angular acceleration is closely related to tangential component of the acceleration. Remember, we have before now that an object moving in a non-uniform circular motion has the velocity, has tangential acceleration, and also radial acceleration. Are we following? So we are saying that angular acceleration is closely related to the tangential component of the acceleration. So the tangential component of velocity, that is linear velocity is given as v equal to r omega. We have gotten this before now, but we know that this is the relationship between linear velocity and angular velocity that we have established before now. So we are saying that the tangential acceleration is related to the linear velocity. Look at the linear velocity here. Are we together? So we have that the tangential acceleration is equal to change in the tangential velocity over change in time. And if we simplify this further, knowing that change in tangential velocity is given by this, we will have that r change in angular velocity over change in time. And change in angular velocity over change in time is equal to angular acceleration. So we'll have this. So from here, we will have that the tangential acceleration is equal to r, this alpha, please. Good. So this gives us the relationship between linear acceleration and angular acceleration. So we have gotten the relationship between linear and angular acceleration. And from this derivation, we got that the linear acceleration is equal to, is given by this expression. And this gives us the relationship between this angular acceleration and this is linear acceleration. We shall be using all these equations we have derived to solve practical problem, for us to better understand the relationship between linear velocity and angular velocity, and linear acceleration and angular acceleration. Okay, the next thing we want to look at is period and frequency. Period and frequency. Period is the time taken for an object exhibiting circular motion to go round one complete cycle. So if you have a stone, tie a rope to it, the time it will take for it to go round to complete one cycle is what we call period. Or period is the time taken to complete one complete revolution. That is the circumference of the cycle. So the time it will take an object moving in a circular path to complete one cycle, we call it period. And mathematically, period is equal to angle over the angular speed. Angle over the angular speed. And when we talk about the angle, talking about the circumference, 2 pi r over angular speed. You know we have gotten angular speed to be given by this expression. So if we simplify this, r, we cancel r, so we'll be left with 2 pi over omega. So this is the formula for what? Period. The time taken for an object undergoing circular motion to complete one oscillation. So if we know the angular frequency that the object is moving, then you will divide 2 pi by it, we'll get the period. Okay, the next thing is the frequency. Frequency is the number of complete cycle made in 1 second. So if you have this object, the number of complete cycle made in 1 second is what we call period. So if you set your stopwatch, you set an object into circular motion, the object is moving in a circular path, completing the cycle until the moment is 1 second. The number of what? Cycle, number of complete cycle make in that 1 second is what we call frequency. So frequency and period, they are related. We say period is the time taken to complete 1 cycle, while frequency is the number of cycle made in 1 second. So they are inversely related. Period is equal to 1 over frequency. So if we have gotten period to be equal to 2 pi over omega, then from here we can have that 1 over f equal to 2 pi over omega. So from here, omega can be equal to 2 pi f. So this is another relationship between angular velocity and the frequency of an object. So I believe you know the mean of period, frequency, and how it is being related down to angular velocity and frequency of an object undergoing circular motion. So let's make progress. We shall be using all these equations to solve problems. Before we go into solving problems, we want to look at centripetal acceleration. Centripetal acceleration. Okay, centripetal acceleration is a center-seeking acceleration. Center-seeking acceleration. As an object moves in a circular path, move with what? Velocity, linear velocity, then the acceleration is directed towards the center, what we call radial acceleration. So a center-seeking acceleration is called centripetal acceleration. So if we have the acceleration is equal to v omega, from here we can have that, but v is equal to r omega. So if we substitute in place of v, substituting this, we will have that this acceleration is equal to r omega times omega. We have not done anything. This expression, look at it here. In place of this v, we are substituting this. So when we substitute, we have this. So we have that centripetal acceleration is equal to r omega square, or v square over r. So please, let's take note of this equation. We shall be using it as we make progress. So before now, we got an expression in the case of linear motion. The acceleration is equal to velocity square over the distance. Then, so we are having this expression that centripetal acceleration is given by this expression. Okay, let's look at some example of how we will use this. Example, let me read out the equation so that we can make progress. A particle of mass 3.0 grams move in a circular path of radius 0.45 meter at the rate of 120 revolutions per minute. Determine its frequency, its period, its centripetal acceleration, and also centripetal force. That is the equation we are looking at. And let's look at it, the solution. From the equation, we have that angular speed given by omega is equal to 1,200 over 60. Angular speed is revolution per second. So let me write the formula. Revolution per second. And from the question, it says a particle of mass 3 grams moves in circular path of radius 0.45 meter at the rate of 1,200 revolution per minute. 1,200 revolution per minute. So we convert the revolution to revolution per seconds. So using the formula, revolution per second. So this is what we have as our angular speed. The next thing is that this angle we can convert it to radians, and in radians we will have that the angular speed will be 20 times 2 pi radians per seconds. So that if we substitute, we will have 40 pi radians per seconds. And from this expression, the angular speed is equal to 2 pi f, the expression we just derived. Using this expression, we'll be able to find the frequency. Remember, the first question says we should find the frequency f. So before we can find the frequency, we need to get the angular velocity. So from here, using this, we say omega is equal to 2 pi f. So from there, if we make frequency subject formula, f will be 2 pi, f will be omega over 2 pi. So if we substitute, omega is 40 pi over 2 pi. So the frequency will be 20 hertz. Is it difficult? No, this is the frequency. So we have answered the first part of the equation. The second part says the period t. Already we say t is equal to 1 over f. So 1 over 20 will be equal to what? 0.055 seconds. Is it difficult? Okay, the C part say we should find centripetal acceleration. Centripetal acceleration. So we have A equal to R omega square. So let's substitute. It will be the distance times 40 pi square. So if you simplify this, you will have 7.11 times 10 raised to power 3 meter per second square. So this is the centripetal acceleration. The last part of the equation says we should find centripetal force. Centripetal force F will be equal to ma. We know the mass of the object, 0.003. From the equation, it says a particle of mass 3 grams. So we convert the gram to kilogram times the acceleration we have gotten, 7.11 times 10 raised to power 3. So if you simplify this, you will have the centripetal acceleration. You will have the centripetal force, So this is the, simplify this, you have centripetal force. Okay, let's make progress. So what is your answer? Simplify this. Let's see. What is your answer? Okay, let's look at centripetal force proper. Centripetal force. The force acting towards the center of a cycle is called centripetal force. It points radially inward. So centripetal force is the force acting towards the center of a cycle and is gotten from the centripetal acceleration. So as object is moving, that force, that center seeking force, we call it centripetal force. And as we earlier said, it is given mathematically as ma or mr omega square, or we can use mv square. Whichever, we can use any of these formula to compute centripetal force. And like we said, is the force that acts towards the center of a cycle. It points radially into the inwardly, it points radially inward. So this is what we call centripetal force. So for circular motion to occur, a net force directed to the center of the cycle or orbit is needed. This net force is called centripetal force. We have earlier mentioned it. And the formula for centripetal force, any of these can be used to calculate centripetal force. Okay, let's look at other example. Let's look at other example. Let me read out the question. An object of mass 4 kilograms moves in a cycle at radius 8 meter at uniform speed of 32 meter per second. Calculate the angular velocity and the centripetal force. So this is another example. Let's look at the given parameter. Given data, we know the mass of the object, 4 kilograms. The radius is equal to what? 8 meter. Then the velocity, v, is equal to what? 32 meter per second. The first question here says we should calculate the angular velocity. Angular velocity. So what is the formula? We have established the relationship between linear and angular velocity before. So based on this, we will use this formula. So angular velocity will be v over r. So if we substitute, we will have 32. V, velocity is 32. The distance is 8. So what is the answer? For what is the unit radian per second? I told us angle, the unit we are using here is radian. It's another unit for angle. Beside the degree, another unit for angle is radian. Okay, the second part of the equation says we should calculate the centripetal force. What is the formula? Based on this parameter, which of the formula can we use? Write the formula, let's see. Yes, this is the formula we are using. Because we know the mass of the object, we know the radius, then we have computed the angular velocity. So let's substitute and see F the mass is 4 kilogram times the distance 8 and the angular velocity. So if we simplify this, we will have 5 Newton. I hope this is not difficult. So this is how we compute either angular acceleration, angular velocity, centripetal force, and whatever we may be asked to look at. Okay, let's solve another example again. Another example, so that with the example for any given problem, you will be able to solve them. Okay, let me read out the question. A stone of mass 0.6 kilogram attached to a string of length 0.5 meter is swelled in a horizontal cycle at a constant speed. If the maximum tension in the string is 30 Newton before it breaks, calculate the maximum speed of the stone, the maximum number of revolutions per second it can make. Solution. So the maximum tension, you know tension is the same as force. Are you following? The maximum tension or force in the string is given by MA. And from here, we can express based on the given parameter, the force, we can use this expression. So we know the maximum force to be 30, the mass of the object 0.6, we don't know the velocity. The distance is 0.5. So from here, making the velocity subject formula, you have 30 times 0.5 over 0.6. So let's take the square root. We are looking for v and not v squared. So if we simplify this, we will have v equal to square root of 25, which will give 5 meters per second. So this is the velocity. Then the second one, we are to find the period. And period, 2 pi r over v. So this is the formula we'll be using. Remember, we said the period is 2 pi over omega. And v is equal to r omega. So from here, omega can be v over r. So in place of this omega now, we substituted this. That is why we have this expression. So let's simplify and see. We have t equal to 2 pi. The distance is 0.5. The velocity, we have already computed it to be 5. So if you simplify this, you will have pi over 5. So we are looking for number of revolution per second. So number of revolution per second is what? Frequency. Remember, we say frequency is the number of revolution per second, or the time taken to complete the number of oscillation the complete cycle make in 1 second. So from here, we have that is given by this expression. And we have already gotten t to be this. So if we substitute, we will have 5 over pi. And this will give us 1.6 what? 6 hertz. So this is the unit of frequency. So in the equation that we are to find that a stone of mass 6 kilogram attached to a string of length 0.5 meter is whirled in a horizontal cycle at a constant speed. If the maximum tension in the string is 30 Newton before it breaks, calculate the maximum speed of the stone. So this is the maximum speed of the stone, and this is how we go about it. We know the tension initially, so from here we are able to calculate the velocity. So this is the maximum velocity of the stone before it breaks up. Then the second question says the maximum number of revolutions per second it can make. That is the frequency. And if we look at the given parameter, for us to calculate frequency, we first of all computed the period. And from the period, we are able to calculate the frequency. I hope is that taken. Okay, let's look at the practical application of centripetal force. We have looked at centripetal force. Let's look at the practical application. Where and where do we use centripetal force? Okay, one of the areas where we use centripetal force is in centrifugal dryer. Centrifugal dryer. The dryer that we use, centrifugal dryer. Centrifugal dryer is used in laundering, and inside this dryer we set clothes. Wet clothes are wheeled at high speed in wire basket in order for the moisted water to leave or dry away. So in centrifugal dryer, you have a basket, sort of an opening, then you put your wet cloth in it. As you continue to swing this basket at a very high speed, you discover that the wet cloth, the water, that the water molecule and everything, as you continue to spin, discover that through this the cloth is dried. So we use centripetal force, which is a center seeking force in a centrifugal dryer. Also, centripetal force find application. It is the gravitational attraction which keep planet and satellite in orbit. In the solar system, we were made to understand that objects revolve in a circular orbit. So as the object is revolving on its orbit, what sustains it is what? The centripetal force that keep the object, even as it revolves on its orbit in a circular path, as it undergo that revolution. Centripetal force keep the object. So we are saying that the gravitational attraction which keep planet and satellite in orbital movement is as a result of the centripetal force. So that is another application. Then the other application, the third one now, is in centrifuge or centrifuge. Centrifuge or centrifuge. It's another area where we find the application of centripetal force. So centrifuge or centrifuge is used in separating suspended solid material from liquid. For instance, in the hospital, is used to separate blood sample, because blood is made up of both a solid and liquid particle. So to separate it, put it in a centrifuge, and as it rotates with time, it will be separated into each different component. So centripetal force find application in centrifuge. Then the fourth one is in centripetal force keeps vehicle traveling round curve from toppling over, because frictional force is exerted outward by the load on the car's tire, and curves on a road or bicycle racetrack are banked or raised at the other edge. So what we are saying, as the car move in a roundabout, it is being kept in position in that circular path as a result of centripetal force. Frictional force may act a way out away like this, but through centripetal force, the center seeking force, it keep the object in a curve. So centripetal force also find its application on the road in keeping a car moving along a curved path. With the help of centripetal force, you see that the car will be able to move. So thank you very much. I believe with this, you have idea about circular motion, have idea about angular displacement, angular velocity, and the relationship between angular velocity, angular acceleration, and centripetal force. Then we have solved simple problems using the equation we have derived. Thank you very much for watching. Please like, share, and subscribe to my channel for more interesting videos.